You think Python is too slow for real-time physics? Think again. Today, we're pushing the Pymunk library to its absolute limits, implementing friction, gravity, and constraints that rival professional engines. We aren't just drawing shapes, we're building a digital universe from scratch. To get this performance, we use Pymunk, a Python wrapper for the Chipmunk C engine. It's the ultimate cheat code. We write clean Python, but the heavy lifting, like collision normals, happens at C speed. Pygame is just our eyes, it renders the coordinates that Pymunk's brain calculates in the background. This decoupling is why we can handle over 1,000 objects without breaking a sweat.
Every universe needs laws. We start by creating a space and defining gravity. The step function is the heartbeat, calculating physics in tiny slices, 60 times a second, to create smooth, realistic motion. First, the essentials. We import Pymunk for the math, Pygame for the visuals, and Sys to handle the window exit. Next, we initialize the canvas a 1000 by 700 window, and a clock to ensure our simulation speed stays consistent across any hardware. Now, the physical laws. We create a space and set gravity to 900. Damping adds a bit of air resistance so things don't slide forever. The run simulation function is our heartbeat. It slices time into 1/60th of a second, telling the engine to calculate the next frame's positions. The main loop keeps the universe alive. It constantly checks if you've clicked close so we can shut down cleanly. Finally, we clear the screen, run the physics step, and flip the visual buffer. We lock the loop to 60 FPS for that buttersmooth motion. And there it is, a complete physical world in under 30 lines of code. When we run that, we see an empty window. Physics is there, but we don't have an object to apply it to, so let's create some. In Pymunk we strictly separate two kinds of bodies: static bodies, the floor, the walls, things that never move. And dynamic bodies, the objects that fall, bounce, and collide. Every body needs a shape to give it a collision area, and a mass and moment of inertia to give it physical presence. Now here's the key question: how does Python simulate hundreds of objects at once without the framerate dying? The answer is spatial hashing. Our universe is set up, but it's still empty. Time to breathe some life into it. First, we import Pygame_util so we can visualize the physics in a moment. Right after that, we define our ground, a static body. It never moves and has infinite mass. We add it to the space immediately. Now for the star of the show, a box as a dynamic body. It needs mass and a moment of inertia. We position it in mid-air and add it as well. Gravity will take care of the rest. Final step. To make sure we see more than just black pixels, we place space.debug_draw directly into our main loop. Only now does the invisible math become visible on the screen. If we run this now we see a box falling on a floor. Now, we're giving our digital world some personality. Physics isn't just about falling, it's about how materials feel. Watch these two balls, elasticity determines their bounce. One hits the floor with a dead thud like lead, while the other rebounds like high-quality rubber. But we're also going beyond free-falling objects. By using constraints like the pivot joint, we can pin bodies to fixed points. This allows us to build complex machinery, like hinges and pendulums, without writing a single line of trigonometry. Let's look at the code to make it happen. First, let's look at our box. In the real world, objects don't slide forever, and they don't bounce like flubber unless they're made of it. We're injecting friction at 0.6 to give the surface some grip. This prevents the box from sliding around like it's on a hockey rink. Next, we set the elasticity to 0.3. This represents the energy loss upon impact. At 0.3, the box will hit the floor with a satisfying thud, absorbing most of the shock. Now, for the ball, we want the exact opposite. We'll set the elasticity much higher, at 0.8. This tells Pymunk to preserve 80% of the kinetic energy during a collision. While the box stays grounded, this ball is going to be lively, rubbery, and stay in motion much longer. But physics is more than just things falling down. The real magic happens when we link objects together using constraints. We're adding a pivot joint here. Think of this as driving a nail through two objects to create a hinge. We define a static anchor point in mid-air and a new dynamic pendulum body. By connecting them with the pivot joint at a shared coordinate, we've just created a physically accurate pendulum with only a few lines of code. It will swing, react to gravity, and collide with our other objects perfectly. Now we scale up. Our final simulation has 3 invisible walls, a floor, a left wall, and a right wall, forming an enclosed arena. Inside it we spawn 2 massive object clusters, a tower of 900 blue boxes on the right side, and a dense grid of 180 orange balls on the left. In the last part, we wrote everything by hand. But if you want to build a big simulation with hundreds of objects, you can't just copy-paste the same blocks of code over and over, it would be a mess. That's why we're starting today by clearing out the clutter. We're deleting the manual setup for the floor, the box, and the ball to make room for a much smarter system. Instead of writing the same thing twice, we're building helper functions. First, look at create_boundaries. This function builds a simple container for us, floor and walls, so our objects don't just fall off the screen. Next, we have create_box and create_ball. Think of these as blueprints. Instead of setting up the weight, shape, and bounce every single time, we just tell the function where we want the object, and it does all the heavy lifting for us. Now, here is where it gets exciting. Because we have these blueprints, we can use 2 simple loops to spawn 600 boxes in a perfect grid instantly. By just changing a few numbers, we can fill the screen with objects that all follow the same physics rules. This takes our script from a basic test to a powerful simulation engine. Let's hit play and see all those boxes in action. Now for God mode. We link the cursor to the physics world using a kinematic body. By attaching a dynamic joint to any object, you can drag and fling them, turning mouse movement into kinetic energy. For explosions, the cursor becomes the epicenter. We calculate a radial impulse for every object within range. The strength isn't constant, it's a linear falloff, strongest at the center and dropping to 0 at the max radius. This follows the impulse formula. In the last part, we built a massive world with over 1,000 objects. But so far, we've just been observers watching gravity do its work. Now, we change that. We're going to implement a God mode to turn this simulation into an interactive playground. First, we need some power. We're defining a trigger_pure_physics_explosion. This isn't just an animation, it's a mathematical shockwave. We iterate through every dynamic body in our space and calculate the distance to our cursor. If an object is within the blast radius, we apply a physical impulse. By using a distance factor, we ensure that objects closer to the epicenter get launched with much more force than those on the edges. Next, we need a way to touch the world. We create an invisible mouse_body. In physics terms, this is a kinematic body, it doesn't care about gravity or friction, it simply goes wherever our cursor moves. To actually grab things, we'll use a pivot joint. Think of it as a physical leash that connects our invisible hand to any object we choose. Now, let's wire this up in the main loop. We track the mouse position in every frame and sync our mouse_body to it. When you left-click, the engine performs a point_query to see if there's a shape under your cursor. If we hit something, we snap that pivot joint onto it. Now you can drag, swing, and toss objects around with realistic momentum. But we want more. We'll add shortcuts. Right-click and the C key will instantly spawn new boxes and balls exactly where you're pointing. And the grand finale? The spacebar. Pressing it triggers our explosion function, turning a stable tower into a beautiful mess of flying polygons. With these few lines of code, we've moved from a static simulation to a fully interactive physics sandbox. The engine isn't just running anymore, it's responding to you. For stronger explosions, I temporarily set the mass to 1, but you can leave it as is if you prefer. Now, let's see how much chaos this world can actually handle. And we see it works. With the spacebar we can trigger massive explosions, with the left mouse button we can move objects back and forth, and with the middle and right mouse buttons we can create objects. Our physics sandbox from part 6 is fully functional, but it still looks a bit raw. In this section, we're going to give the simulation a professional polish and make sure we can keep a close eye on performance. First, let's clean up the visuals. We'll define a specific font for our HUD and adjust the render flags. By default, Pymunk draws everything, including joints and contact points. We'll limit it to draw_shapes to make the scene look much sharper and less cluttered. To know exactly what's happening under the hood, we need a dashboard. We're writing a small helper function called draw_HUD. It retrieves the current number of active shapes from the space and calculates the FPS from our Pygame clock. This data is then rendered as a text overlay in the top left corner. A function is just a blueprint until you call it. Right after space.debug_draw, once the physics world has been rendered, we trigger draw_HUD. This ensures our statistics are drawn as a clean layer on top of our simulation. From a blank canvas to a fully interactive physics sandbox, in pure Python. And this is just the foundation. You can take everything we built today and push it further, a puzzle platformer, a destruction derby, a ragdoll simulator, or even a reinforcement learning environment where an AI agent learns to navigate a world you define. The complete code is in the description below. If this video taught you something, drop a like, it genuinely helps. And subscribe if you want to see what we build next. See you in the next one.